Okay, so welcome guys, welcome to the latest Learn-to-Earn session with Lawrence. Today, Lawrence is going to talk about recursions and advanced data types. I'm sure that you are going to enjoy it and you are going to learn lots of things related with these stuff that is also related with Mina ecosystem. So please, Lawrence, take your stage. Thank you.
Okay, thank you. Hey everyone, I hope you're all having a good day. Yeah, welcome to session number 3. Let me present my screen. Is that working? It is good. All right. So the third session. So recursion. I think we're doing some advanced data types, but we did some already, so I changed things around slightly. So apologies for that. But anyway, we are making we're getting quite the way through these sessions now, so that's all good. So what I've got for today is to talk about. We'll do sort of what's new, just to catch up on what's been happening. Then we'll talk about recursion in some general sense, so looking at use cases of recursion, and then we'll look at it more specifically and how to do it, really get into the nitty-gritty. Then we'll look at custom tokens and look at an example of ECDSA, which is something new that we've had. So that's the plan for today. I'm not sure how long it's going to take. I think it could be a little bit of a shorter session today, but we'll see how it goes. All right. There's a link there to Slido, so please use that to ask questions. That's helpful. If you could put questions in there, because I tend to miss things if they go into the normal chat. All right. Now, before I start, just a couple of things that have come up since last time. One about the challenge. I do apologize. I think the way I'd written the challenge was a little bit misleading for people. So people have been asking about whether they, I think with a particular function, whether they can have more than one parameter. Yes, that's certainly okay. So please write it in a way that is going to work for you. We can be flexible about that. I'd written it badly. I didn't mean to say that you're restricted to just having one parameter for all the functions there. So yeah, please just write it so in a way that's going to make sense. It's going to work. That's that. Also, yeah, you don't have to do any kind of a UI for that. I was just looking for the contract side, because otherwise it would be a little bit more work. So yeah, I hope that makes sense. But as always, please do ask either. You can ask on Slido or on Discord. Either is fine. Now there was a question from last week on Slido that I wasn't able to answer at the time, and I still haven't been able to find the answer. I don't know who it was from, but someone was asking, was there a subcurve that could be that was possible on the pasta curves? My answer is I don't know. I was trying to find out, but I haven't managed to find anything. I think they were asking, was there something similar to the baby job subgroup and curve that is available for on Zcash, but I haven't been able to find anything. I'm sorry. I'll keep looking, but I'm afraid I haven't found anything so far. Okay, so let's have a look at what's been happening, what's new. So the test network has completed now. So this started, I think it was back. Maybe it was back. Was it back in October? It seems a long time ago. But yeah, it's been going for quite a while. I got involved and was running some nodes for this, and it's ran until December, I think, and then it got extended. And so it's been, it's just been there for testing and stress testing and that. But yeah, that's all completed now, so that's good news. Everything has finished with that, so that's the next step completed with that. Also, there was an announcement about this punk poll who are partnering with Mina, which is a a voting platform that has censorship resistance. Obviously, all the aspects that you'd expect from being able to do this on a blockchain, and particularly Mina. Also, there was the security audit of Pickles. I think that has just come out, and they. So I can't remember who did this now. But it's the upshot was that there was no. Least authority, of course. The upshot was that there were no major problems. So again, good news for that. All right, so let's start talking about recursion. So as always, with these sessions, what I would like to do is to try to introduce you to things maybe that you haven't come across in the project that you are doing for the program, just to widen your experience and give you an idea of other things that are happening, so that these are things that be able to take forward and could be useful for you. And with recursion, there's quite a lot kind of general things to think about it. I mean, recursion, that obviously that's very much at the heart of Mina. I mean, that is what Mina is all about, and that's how Mina came about, and the fundamental sort of technology behind it, and what allows us to have a succinct blockchain is the fact that we can do recursive proofs. So it's obviously it's very important to that. But that has that possibility then has allows us to do things. It has knock-on effects, and it's worthwhile thinking through some of those ideas. And one of the great things about Mina, one of the big advantages about it, because we have this succinct blockchain, this means that we can this gives us more or wider involvement. More people can get involved, checking the chain, and the hardware requirements to do that are much smaller than you may need on other chains, because you can even run a node in a browser. So that is a great democratization of the system, and it that means more people can get involved. It builds a bigger community. There's lots of positives because of that. And further to that, there was a recent article by Vitalik that I thought was interesting, because it was saying things that I think really sort of chime with the way that what's happening with Mina. But one thing he was talking about was he was contrasting how blockchains, or what they were like before kind of 2017, I guess, and where there seemed to be quite a move to financial applications on blockchains, and away from and sort of more of an emphasis on that, away from other types of applications. And he thought part of this is being driven by the size of transaction fees, the fact that if transaction fees are high, then only certain people will be able to get involved, and those people will probably be involved because they are doing financial transactions. And where we have other types of applications that maybe are more to do with social good, which perhaps will work if there are low transaction fees, then those people are going to get pushed out of the system if the transaction fees are too high. That use case won't make so much sense. And so really, I think that was a call to try to sort of keep down transaction fees, the importance of scalability. And as part of that, he was talking about ZK as being an essential technology. So all of this, I think, very much chimes into what we have with Mina. I mean, obviously we've got the ZK side, but then also the fact that the way the transaction fees work, with the transaction fees, we don't have the same problems with network, or it's not as determined by network congestion on Mina, but also there is going to be a lower limit to the fees that are involved, which is going to be determined by the cost of the participants in the network in supporting the network, because the block producers, etc., need to be rewarded. And so the way the sort of the economics of that does give a a kind of a lower limit to how, what we can do with transaction fees. But then, because of the way that Mina works, I think we have an advantage, and I think this means that we're not facing the problems with higher transaction fees that other chains will face, because because we have the the execution part can be done off chain. So this is a great benefit for the scalability as well, and it reduces the load on the network. So all of this, I think, means that with the types of use cases we have on Mina, that we can have more greater participation, in potentially a larger community getting involved, but also the type of involvement is going to be, I think, much wider, more diverse in terms of the applications, because of the sort of unique features that we have in Mina. So yeah, really all good things. But I thought it was worth talking about this and really allowing you or pointing this out, so that it's something you can think about, especially when you're building, so that you can take advantage of these types of things. And you can potentially build projects which will have potentially low fees. Okay. Question on slide: are we going to have feedback about the challenge? Not today, because we still have we still got a few days to go before the end of the month. I'll have to get back to you actually when that's going to happen. Yeah, I'll get back to you about that, but we will have a session where we'll have feedback about the challenge. Yeah, we will do that. And we'll introduce the next challenge as well at that point. Okay. Sorry, but carry on. So talking about recursion, and recursion has become, well, one of the things that originally attracted me about Mina was that they were really championing a technology, the idea of recursion in zero knowledge, much more than other systems seem to be doing. And really, they had gone out and said, we think this is we've got a really good use case here, and they were following it. And it seemed that other systems weren't really taking advantage of this. And then certainly over the last couple of years, we've started to see this being picked up much more. And one of the ways that this has been happening is as ZK rollups have been introduced. We've got layer 2s building on Ethereum that are using ZK rollups. It has been important for them to be able to aggregate proofs, because what the typical way they work is that there would be a batch of transactions coming in, and the initial way that these tended to work was that they would wait for the whole batch to arrive, then they would try to build a proof that all of those transactions were correct, which involved a sort of quite high memory use, and it was quite inefficient, because you were having to wait for the batch to arrive before you could start the proof process. So what people then tended to do was to move away from that and try to do a more of an incremental approach, which meant that they would start to produce smaller proofs as transactions came in. Maybe they would have a proof of one transaction, and then they could try and aggregate that and join proofs together, so that you would have a proof of a few transactions, and you would carry on building up these proofs as the batch of transactions arrived. It meant there was a kind of a parallel processing going on, and it made the layer 2s who are doing these kind of roll-ups much more efficient as a result, because they could take this recursive approach to proofs, and then they would end up with all of these proofs being built together into just one single proof at the end, as before. So this whole idea of recursion certainly has started to be used much more, and in terms of research as well, it has been a very productive time over the last couple of years. And I've been to a few conferences, and I've asked researchers in this field about what's your favorite technology from the last couple of years, and a very common answer I get is about things like folding schemes, such as used by Nova. So this whole area of recursion is very important and certainly very widely used, and there's a great appetite to understand it and develop it further. Okay, so that's really I'm trying to set a background, I suppose, setting the stage for what is happening. We already, I think we're spoiled a little bit in Mina because we've already got this going on, and we can, when we're building, we can then also use it within our projects as well. So we'll look at that, sort of dig in now, looking more at how we can use it when we're building, and the way that we can use it. One of the in addition to what we sort of have in the background with the succinct blockchain, but in terms of the programs we're writing, what Recursion allows us to do is to split computation into smaller parts, and then join these together using Recursion. And the way that these can be joined together can be quite flexible. So we can split out our computation into very kind of standardized pieces, and we need to do that because there is a limit to what we can do with a in a circuit. So what we can do is to create these very standard pieces that will fit with the limits of what we can do with the circuit, but then use Recursion to join these pieces together until we get the final proof that we want. It also means that you can sort of respond in your program dynamically to the what is happening. So you're not having to really fix your program and the kind of the limits of what your program can do, and decide all of that up front. You can use Recursion to sort of adapt somewhat dynamically as people are using your program, because you can produce multiple proofs and then dynamically bring these together. And also it allows us to sort of allow more flexibility in how we create the programs, and as I say, with variable number of arguments, for example. Okay, so let's dig into it a little bit further. And the heart of this is the ZK program. And I think the last session, the last week, I suppose, we just spoke briefly about this and said, really, I mean, this is the heart of what we're building. But we looked at this. We said that the ZK program, the difference really is that this is kind of independent of the blockchain context, that this is sort of this is very much about the circuit and the computation, and we then we have the smart contract, which then sort of brings in the context around that. And so when we're building and doing recursion in our programs, we're very much going to be using the ZK program and then the proofs such as the self proof, and then obviously we can then use that and get the we can then put that, we can also put that into a smart contract and then have that verification being done and have that being done on chain. So so we're going to concentrate on the ZK program first of all. So the first thing about that, the inputs private by default. We have flexibility about what they're going to look like. This is a very simple example of a very simple ZK program that you could create, where we just have we're just taking in one field, and then we're when we run this, we're just testing that that is going to be equal to a certain value, and then the way that we can use that is what you can see here. Once we can compile it and then run it, and that will give us our proof, which we can then verify, as you can see here. So once you've got that, then you can pass that proof to be verified. So here we're passing it into a smart contract to be verified, and the alongside that, we can then pull out values as well, as you can see here. So we can pull out the details of that particular field also. Okay, so that's just a very simple example, but it shows you the general sort of process we can go through. So we have the ZK program here, which is doing some computation, or in this case, we're really just doing some little check. From that, we can create a proof, and then we can verify that proof. And of course, within your smart contract, you could be taking in, you could have this proof, and then you could also then do another proof later on, and so on and so forth. So if we think about recursion and how that works generally, recursion is in general will have two parts. There will be a base condition, which is really where the recursion has ended in some ways, and then a step, which is sort of stepping through, sort of iterating through or stepping through and doing the next piece of recursion, or going from kind of one recursion to the next. And so I think I showed you this pattern last time, but I'll just show it again, because it shows this split that we can have, in that we have our ZK program as before, but this we've split this out now into two parts. So we've got the base case, which is where effectively our recursion ends, and we're just doing an assert there, and then we have the step part here, which is taking each time we're doing this step, what we're doing is we're taking, in addition to the inputs, or the normal input here, this field that we're passing in, we're also taking in a proof of the previous step that we had, and then this is being verified, and then we can go on to the next step by going to add. So this is adding an extra value. So we add one, and yeah. So this is all the next step. So we're checking that input from we're checking the input from the earlier proof there. But that is our step, and we're doing the verification of the previous proof. Sorry, and then we're checking the details from the previous proof. I also put that into a gist, as it's perhaps a bit easier to see. But the way then that we tie these two parts together is this thing here. So this is how we get the recursion happening. So as before, we do the compile, and then we can do our base case. And then we can start doing a recursion here. So we start off and we create a proof with the step, but this proof is taking as an input the proof from our base case. So we add that in, and that gives us our proof 1. And then the next thing we do then to produce proof 2 is we take proof 1, and then add that into our step function, and that gives us our proof 2, etc. So you can see that this is where the flexibility of the recursion comes in, because we have our kind of fixed pieces in our ZK program here. We have the base case and the step, but then the way that we are actually getting the recursion happening is in this part here, where we're going through this, and we're calling this step and passing in the previous proofs that we've created. And so you could see that you could make this quite flexible by just calling this as many times and as many more times as you need, and at each point you'll be passing in the proof from the previous time that you call the step function. And then once you've done that, you've got your final proof. Then obviously you can put that in. That can be that can be verified as part of a contract as well. Okay, and And I've got some further examples here. Let me just have a look. I thought, yeah, so there's a more complex example here with a voting function. Let's move to the, let's find it. So here you can see your ZK program. So this is where you can you see the different parts, and so we have two things here: the create and the apply vote. So here the create is our base case. This is our starting point, and then the apply vote is effectively our step function, where we then take in the proof that we created earlier on. So you can see here we've got the self proof, the earlier proof here that we've created. So this is what we can do. We can call this apply vote multiple times, and also the first time we would do it after having done the base parts here, and so you can see you can see this getting called somewhere. Yeah, I've lost the beginning of this. So this is setting it all up here. Yeah, you'd get the there you go. There's the create, and then you can see, for example, here we've got vote 1 on line 53, where we're doing a vote, and so on. We can do. Sorry, we also on 54. We can do the apply vote, passing in the proofs, etc. And we can keep going there. Okay. So, do we have to pre-compute proof? Yeah. So, so this would be pre-computing your proofs here. So this would be the part where you're creating your proofs, and then you can pass that in to a method in your contract. Yeah. All right. Other things that are available within from self-proof, we have this verify if method for conditional verification. So you could, I don't know if I've got a. Yeah, so you got the example here. Sorry. So this allows you to make a decision whether you are using, if you want to verify or not. So here we're passing in a proof, and then we also have the idea of this a boolean for it being recursive, and also there's the dummy, which gives you a dummy proof if you want to. If you have an example where you may not be using recursion, and you just have a base case, you can use that dummy proof to pass that in there. So it's just makes it a little bit more flexible there. There's another nice example here of using this in a game. Let me open that up. So as always, thank you to all the people whose code I'm showing here. I'm very grateful to all of those people. So anyway, here you can see we have our ZK program again, and we have some methods. So here we have the base case is the start game here, which is setting up details about the game. So setting up IDs, etc. And then the step part of this here is this move part, where we take in the proof here, the previous proof. So this is the part when the game has started, and then people are starting to make moves, and we're taking in a proof that the previous state of the game is correct, and then details of the move that the player is now making, and yeah, so you can see that being done there. Also you can see here the use of hash functions. So very common in games, using hash functions as for a sort of commit reveal, so that you can sort of obfuscate details, etc., and then check that, check the correct commitment there. Okay, but that's just an example of another example of it being used in a game. So so the base case is the initial setup, and then the step part is when they're making a move. So the question: can recursion replace encrypted off-chain storage? So I don't think it's so that's not really its design, I suppose. Recursion is more general. It can be used for off-chain storage. So I've got I've kind of got an example, but we'll talk certainly more about off-chain storage next week. But it's not. They can go together, I suppose. I'm not sure it's exactly a replacement. So I'm sorry. I'm not sure how to answer that otherwise. This next example I have is about showing how you can sort of set up the recursion in quite a structured way, where you are representing the computation as a tree, effectively. So there's I think there's really kind of a subtle difference between this and sort of regarding this as a kind of a data structure. I'm not sort of saying that. It's more a case of how the recursion is happening. And but what you can see here is that our base case is just is setting things up, but then the step function here, what we're doing is we're looking at pieces of computation as being the sort of the next parts in the tree. We've got a left and a right, so we're taking in proofs from a sort of two computations and verifying those, and then that gives us the next level up in the tree. So it's a way of sort of building up computation in a kind of a tree-like structure. So that pattern may be useful for you as well. Here, so the other thing to say, I spoke earlier, and I was talking about verifying this in a contract, but of course that may be well what you want to do, but it's not. You don't have to do that. You can also, if there may be the use case that you want to verify a particular proof off-chain, so you can also do that. So here's an example of how you can do that. So you're creating the proof here for a simple program as before, and then using the verify here which takes in the proof and the verification key, and can just do all of that off chain. And so you can, you get this okay coming back to say that's a valid proof. This kind of thing as well may be a useful pattern for you to use generally. If, for example, if you have some logic, you're building your project, you have logic that you want to try out, and if it's not necessarily dependent upon sort of blockchain features or aspects of the blockchain, then it can be quicker to do something like this rather than to be testing this in a contract, because you've got the overhead of the chain to think of and the transactions, etc. So this may be a shortcut that you can use when you're sort of initially designing and testing out sort of small pieces of logic, etc. Okay. All right. So I hope that gives you an idea of how you can use recursion generally. You can really just sort of build upon some of those ideas, I think, and hopefully those examples will be useful for you. I've seen a couple of example of errors that people have found, so I just wanted to highlight those in case you get these. One thing, you do need to make sure that there is some sort of final step to your recursion. You can't just carry on forever, otherwise you're going to get you're sort of doing an infinite loop effectively, and you will that will sort of go past the call stack size. So you'll get something like that. So obviously you do need to have a way of stopping your recursion. Also, when you're doing the recursion, the step you take, that should be really the structure of that, particularly the circuit, should be independent of the sort of the iteration. You shouldn't be changing that as you're iterating through, as you're going through the recursion. Obviously, you can pass in new values, and you're going to be passing in different inputs, but you don't want that to change the sort of the structure of it in a fundamental way. If you do that, then you'd get something, an error looking like that. And then finally, there's been a recent issue looking at when using recursion with if you're doing ECA DSA, or an ECA DSA circuit. But I guess that will be fixed. But just to be aware of that in case you come across an error. There's for further reading, there's looking at recursion in general. There's a post there from Brandon talking about pickles and the design of that, and then comparing that, or looking at in the context of some of the recent advances in folding schemes such as Nova. So that's more of a general sort of or a background cryptography article. And then Ilya, I don't know if he's I know he's sometimes on this calls, but very active in the community. He's done a great blog including an example of a calculator that uses recursion. So okay. So have a look at that. It's a very nice. There's some very nice blogs there. Okay. So that's all I want to say about recursion at this point. But please do ask further questions if you have them. It's a very powerful tool that we have, a very powerful addition to what we can achieve when we're writing our programs. Okay, so I'll go on now to look at custom tokens. So there's a link there to the documentation about this, and it is a little bit complex, the way that these work. So I'll try to take you through how they work and some of the concepts and some examples of how to use them. So they with the concepts that you need to know about. One of them is this idea of a token account, which is it's like a regular account, but you're holding a balance of a custom token instead of having a balance of Mina, which I guess we're more used to. Oh, sorry, I'll just look at the question on Slido. Does recursion increase the size of gates or constraints of the cumulative proof output? No. So the idea is that if I just go back, let me find go back to the original this original thing here. So really what we're doing is we're each time we're doing the recursion, we're taking, we're calling this step, and we're taking in the proof and then verifying it. But then that's all of this code is really part of the circuit. So each time we call this, we're not changing what the circuit is doing. We're not changing the circuit itself. We're just passing in a proof, and so that doesn't affect the size of the circuit. We're expecting this proof to be there, and the output of this is then going to be a proof as well. So as you go through and do create your proof 1, proof 2, etc., these are all going to effectively be the same, because the the circuit that is being used to do this is just this each time. It's the same. Sorry, not the base case. The step. It's the same thing that we're doing. It's just that we're passing in some different data, different proof each time. But yeah, the size that we end up with, these are all going to be the same. Is that the reason why the Mina blockchain size didn't increase over time? Exactly, yes. So that's why we get a succinct blockchain, is the fact that what we're doing when we are creating a proof for the latest block is that we pass in a proof which is a proof of all the previous blocks. We also pass in input of the details of this block, and then we output a proof of those things together. But that step that we do to prove each block really is a fixed thing. It's a fixed thing which includes a verification part inside the circuit. Yeah. So yes, it's the same idea that is being used, and I think that's the fact that was at the heart of the way that Mina works, sort of in the blockchain sense, is why we're able to do this when we're looking at writing programs, because all of that sort of functionality is already there. We've already got these things available to us, so we can then do that within our code as well. It's applicable then to sort of their 1JS. Yeah. Okay. So let me go back to the custom tokens. Okay, so yeah, so the token account, this is going to then have a balance of a specific custom token, but it is differentiated from the normal account in that it depends upon a public key, but also a token ID. So that is then it is specific to a particular token. And if because you need this specific token account, then if you receive if an account is going to receive a custom token, but that account does not exist, then that will get created. And yeah, so that's what I said really. So token accounts are specific for each token custom token that we have. So for a particular public key, we could have multiple token accounts. Now there's also this concept of the token owner account, which is there to enforce how this token is going to work, and gives us all the functionality that we expect for a token. So yeah, that's the governing account for a specific token. And there's some details here of what you can do with a token. That's just from the docs. You can see that. So let's look at how this is used in. So I said that there would be a this account will get created to govern the custom token, and this account then has the privileges or the permissions to do various things with the token. So obviously there's permissions around this. Sorry, let me just, I've got to unfreeze my screen. Sorry. Get back to Slido. Oh, just a second. There we go. Sorry. And so this token owner is the account that is going to be involved in the major functionality for a custom token. But also it is involved then for sending tokens, and this makes it a little bit more cumbersome, I guess, because this this token owner account has to get involved when you're sending tokens between accounts. So the token owner needs to approve the transfer of these tokens between the account, which can be done in a couple of different ways. The way that this approval can happen can be done via a signature, or it can be done via a proof, and I'll go into details of that more in a moment. The question about, can I go through the tree-based program design with Recursion again? Yes, I will. I'll finish off the tokens, and then I'll go back to that, certainly. Okay. So yeah, so that's the token owner. So this is the account that is controlling a particular custom token. And then the token itself will have a certain ID, which is a unique identifier that is created, and you can find that on the token. So if we want to create a token, then we need this manager contract that is going to be owning the token and is going to be responsible for the functionality around the token, and also has details about the symbol. And so what that token owner potentially can do are things such as minting. Obviously, this is if you're going to use a token, you need to have a supply of that, so you need to be able to mint a token, and so that process is very, it's a very straightforward process. The concept is similar to things you'll have seen. The idea, you call the mint method on the token, and you give it an address that you're going to send tokens to, and you give it an amount, and then it will mint that amount of tokens and send those to the address. Similarly, you have burning, which is able to remove tokens from the supply from a particular address, and then we also need the possibility of sending tokens as well between accounts. So this token owner needs to be able to, or we need to have this method that will allow us to send tokens, as you can see here. Yeah, that's what that looks like. Okay, so so I said that these methods are available, but it's clear, I think, that you wouldn't want anyone to be able to do this. There has to be some type of authorization involved, and so that's what the token owner is doing. The token owner has that authorization, and as I said, it could be that authorization can be in the form of a signature or a proof. The way it works with the signature is the simplest, but it is in some ways less flexible, because what has to happen if you have people trying to send tokens between accounts, then the token owner needs to sign that transaction to say that they approve this the sending of the tokens, and so that introduces some synchronicity, I guess, between the participants. They have to have the token owner signing this transaction before they can submit it to the network. So there's a dependency there between the different actors involved. As I said, the contract will have a send method, which is actually doing the sending, and so what it looks like is, or what the signing looks like is like this: is that your app is trying to send the tokens, send from and to a certain address and a certain amount, and then we have to have the token owner signing this to approve this. Once that's happened, then we can actually send that transaction off to the network. And don't, it's confusing, I know, but this send here is not has nothing to do with the send tokens. This is the transaction being sent here to the network. Yeah, that's that's, as you can see, that's simple in terms of what do we need to do. There's not very much code that needs to be involved, but it's annoying that we have to get the app to sign that at that point, and it's before the transaction could be sent. So the other process is to do this with a proof, but this is more complex. But what the way this happens is that the application that wants the authorization to send the tokens needs to provide a way for the token owner, so the account that is responsible and for authorization. They need to provide a way for that account to inspect the changes and verify that they are valid. And then that token owner can inspect the updates, and it could, for example, have some type of rules. You could decide that you're going to freeze certain accounts or something like that. So this is to allow extra functionality from on the token owner side. So the parts or the code that you need to use to do this are the callback and the approve, and these are the steps that you need to make. So you have to create the updates that are involved in making this transfer that you want to do, and then you have this callback function which involves these changes, and then the token owner can use the approve to execute that, and at that point can apply any sort of specific sort of custom functionality that they would like to do or like to be involved. So they could at that point reject this transfer if it contravenes a certain rule that they have. So that sounds a little bit complex, I know. The best way to understand it is to see an example. So there's this example here. So this is an example using a proof. So you can see here. So let me talk through. Unfortunately, I can't split my screen easily. But what it is using is, we have the CK app B, which is wanting to send tokens between to a particular address, so this here, so they're wrapping. So this is the callback part here, line 56 onwards, and so they're saying that they want this, this approved send to be approved. They're saying the amount for that, and they're calling the details here for the send tokens, and then this is this send token. So this is the send tokens is then being used. This is the token owner here, or the thing that is controlling the tokens. So this then can approve that callback, and it's looking at the different details from that update that this transfer is going to make, and it can adjust those, or it can make the changes. So that's it's a little complex, I know, but that's the way that these things fit together. So have a look at that code anyway. It should make sense. I had another example. Let me have a look at that. Yeah, so another example of doing that with a proof here. this is more of a complex one. I think yeah, so you can see here, this is where we create the callback and do the send tokens. And I guess earlier on is where here's a send token. So here's where that piece is being approved. Okay. All right. Let me just, okay. So that's the other method. So we have two ways to get the authorization if we want to use custom tokens, either by signing the transaction or adding a signature to the transaction, or by having a proof, as you could see there. So some further examples here are. I'll just go through some of these. I think I tried to get some sort of simpler and then more complex examples. So this is a very simple one, where, as you can see here, we've got the we're initializing our state here and adding in a setting the symbol for this particular token. We're setting the amount in circulation, so that's part of our blockchain state here, our total amount in circulation. So we're initializing that, and then we have a method to do the minting. So for that, we check we've got the correct amount there. We then verify that this is from the correct person, and then we can do the mint, and we mint to a particular address, and we mint a certain amount. And once we've done that, then we need to update the new amount in circulation, because that's changed. So that's where we do the set there. So a very simple one. So we have the mint and send tokens. We don't have a bird in here, I guess. Okay, but that's a very simple example. Oh yeah, so to the way that you would interact with that, you can see here. So you you're setting it up here. You're doing your minting. You decided you're going to mint 10 there, so that will do that, and then you can get the updated amount in circulation, and you can print that out, and you can do a simple send of tokens as well here, as you can see. Okay, and a larger or a fuller example than that is in this project. Again, thank you to people whose code I'm showing here, but this gives you a more realistic example of the types of things that you want to do. But you can see again, we in this case we've got other things that we need to set up initially, such as the number of decimals, maximum supply, when we have a minting and a burning, and then we have details here of the callbacks again. Do take note of the comments here as well, in the way that is detailed, but it does show you certainly the other pieces of state that you may well want, the other pieces of metadata that you could want in your token. Okay, so that was another example, and I also just wanted to show you. I'll give you a link to these tests here, where, because I think the previous examples were involving this being done, or they were involving contracts, whereas this here we're using normal accounts. So there's further examples that you can see. I think this is all from the same project. Okay. Question: can token transfers be approved automatically based on whatever rules? Yeah, so that's this example is best, perhaps. Yeah, so that's the idea. Oh no, that's not a good example. The previous one I think was better. Yeah, this one with the proof authorization here. That's what this is doing. So when it does this send tokens, it's doing the approval of this part here where we had the callback, and it's getting details of what is happening within that change when we're changing, we're updating the transactions, and yeah, it's doing those updates then based on that. Yeah. Okay. All right. Let me just. Okay, that's okay. Right, and then we can take this even further. So there's more. You can, if you look in the documentation, there's also examples, because these types of examples are the ones, the sort of use cases we typically might want to do. So this one is an example where we're having some whitelisting happening. So we're allowing certain accounts, and again, for the token, we do set up some metadata as well. But we also have this. We also have a Merkle tree that we are using, which is being used to hold our whitelist. And excuse me, as is a sort of the common pattern with that kind of off-chain state, where we're holding the root of that tree as part of our on-chain state, and then obviously we can update that and then post that the latest root, update that on chain. So you can see here. So that the first part is initializing our token. The next part is to mint that. So this really is what we've seen before. But then here we've got the code where if you had a whitelist, you could be adding to that. So the usual types of things you want to do, you're checking that we've got the correct root, that we're allowed to do this, and then we can create the new root and then set that within our state. So that's the way that we do that. And then for the actual process of sending tokens, we have this additional part that once we get our whitelist, or we've got our root, but then we're also passing in our the witness for that Merkle tree, and then we can check. We can check the Merkle proof from that, so that we know that the I think it was the receiver address is allowed to receive these tokens. So we're checking that is part of our whitelist, and then if that's okay, we can actually do the sending of the tokens. All right. Okay, so that's an example, and then to interact with that, there's details here as well. So this is all sort of straightforward here, but you can see here we're creating our tree that we're going to be using for our whitelisting, and we're getting details for a particular leaf in that tree, etc., and then sending off to various accounts, etc. Okay. All right. How am I doing? So we're got a little bit of time left. All right. So let me go on to ECDSA. So I said I was talking last week about this being a recent addition, this gadget, and this is useful because it allows interoperability with Ethereum, because Ethereum is using a different signature scheme. So it's using the ECDSA for its signature scheme, and the So what this allows us to do is to take signatures. So you could take a transaction from Ethereum and then verify that signature. The way signature verification happens is that you take the message that is being signed, you take the signature, and you take the public key of the person who has signed that, and then you pass that to a function which will, from those three pieces of data, bring back a true or a false as to whether the signature that you've provided is correct for that particular message and for that particular public key. Okay, now, so that's the general way that we do signatures. With this particular gadget, we have a little bit of extra things we need to do up front. So you need to initialize it with a particular configuration. So you have this idea of curve parameters. Now, we're a little bit, we don't have much choice really, because we have the pasta curves or the Ethereum curve at the top. So we don't have a lot of choice, but we do have, the choice there. We can use that as our signature scheme. So we need to do that first of all, and then we can create an instance of that. And once you have that, you can then use that to check a signature. So this piece of code here is just an example of a signature. So it's creating a key pair first of all, but one based on the Ethereum curve. It's then getting a message and signing that, creating a signature from that. Now, this first part, the creating the signature, is not provable, and this kind of makes sense. You don't really need to prove that. What you're interested in is the verification of that signature. That's the part that is provable, and so for that you have this use verify method on the signature. So you pass in to that, as I said, the original message and the public key. And obviously you're doing this from the signature itself, so that's where you have the signature, and then this will bring back a boolean to tell you whether that's a valid signature or not. And here is an example of that. A more complex one. Yeah, so you can see here we're creating the message and doing a verify. Also, you can see doing analyze methods here to show get details about this particular circuit, etc. Okay, so a slightly more complex example there for you. There's also, you can do more things. So I've just put out showing you the API here of the other things you can do. So you see some of these within those examples. The fact that you can create these types of key pairs, you can sign a hash of a message, and then there's the verification and the signature part there. Okay, so that's that. Let me just go back to the question someone had about this idea of the recursion tree. So what what this was about was the idea that you would be going through a tree, or you would be organizing your recursion as a kind of in a tree structure, where we start off the base case is just the I guess the initial part there, there's nothing really involved with that. But then the step part, what you do is you take in two proofs. So you take a proof from the from the point you are in the tree underneath you, the left and the right, and you verify each of those, and then that will create a proof of the particular place that you are in the tree. In this case, what we're doing is we're saying that we want these things to the details from each of these pieces of computation. So from the left, the inputs of the left and the inputs of the right, we want to add those together, and we want to know that that's the details that we have at this point in the tree. We're just adding up items as we go through the tree, but the way this computation is being sort of organized is that we're doing it in a kind of a tree structure, and verifying the left and the right parts as we go through. I think there is a limit to the number of proofs that you can have in this step, but I can't remember what it is. But I think that is limited. I don't think you could just sort of expand this indefinitely. I think there's going to be a point where that is going to be too big for us to build a circuit out of this part. But yeah, that's what that's about. So I hope that answers your question. Okay, so that's everything. We're finishing a little bit early, but I hope that was useful for you. Next time, we're going to be looking at storage solutions. So this is going to be quite a big topic, I think, because this is, a very common thing that people need to do. So yeah, there's quite a lot to talk about there. So I'll stop sharing at that point. As always, if you have questions, you can ask them on Slido or on Discord, and I'll be happy to answer those. So thank you all for attending, and hope you have a good week. And I think our next session is next week, so I shall see you then. Thanks, everyone. Bye-bye.
Thank you so much, Lawrence. Thanks, guys, for attending the meeting to this session right now, today. So let's see you again in the next session, as Lawrence say. Bye-bye.